Okay, so I will tell you about an interesting story about of Zamolodchikov periodicity. Zamolodchikov periodicity. Okay, I hope everybody can read the board. If you cannot, there is nothing I can do about it. That's as good as my camera gets. But I think it's okay. Uh, okay, so basically the backstory is I know many of you probably heard a course already about cluster algebras. So when cluster algebras were discovered, actually many people were initially skeptical of them. They were saying, what can you prove which you couldn't prove before? Okay, so and actually the first thing which people could prove using cluster algebras, which they couldn't prove before, was Zamolodchikov periodicity. So it was like the first triumph of cluster algebras, the first victory kind of. Okay, so but let me start telling you what's it about, and we'll start on a very basic level. Uh, so let's take a path. Let's take a oh, hopefully. Okay, let's take a path, and we will color it black and white. So maybe and the last one is black or white. So it could be a short, could be like just like two vertices. Uh, we take a path, we put a number at each vertex. So something like this. For example, if this was my path, I could put x1, x2, x3. And now I start doing some kind of transforming those numbers. And the rule is like this. Start changing xi into product over all neighbors j of I, right? So product over all things connected to I in our graph, xj plus 1, and all of this divided by xi. Oh. And do it first for all black vertices, then all white vertices, then for all black vertices, etc. Okay, so this will be our dynamics. We will start with some numbers on our path, and we'll start following this rule, just changing. First, we change black numbers, then we change white numbers. Okay, let's try it. Let's try it. So here, let me see where yeah, let me try to just do this example over here. So this will be our example. Let's start with numbers 1, 1, 1. What happens on the first step? This 1 becomes what? So 1 becomes 1 times 1 plus 1 divided by 1. So it just becomes 2. And those two guys stay 1. Okay, so far so good? Yeah. Okay, now we need to do the same to the two white numbers. So each of those ones, what happens to them? 1 becomes, there's only one neighbor, 2. So it becomes 2 plus 1 divided by 1, 3. Yeah, so far so good. Okay, and then we keep going. So on the next step, what will this 2 become on the next step, right? Now we do the black one again. What does this 2 change into?
5.
5.
That's correct. Yeah. So 2 changes into 3 times 3 plus 1 divided by 2, which is 5. So it becomes 5. 3, 3. Then each of those threes, let's see what happens to the threes. 3 changes into 5 plus 1 divided by 3, which is 2. Wait, is this right? 3 changes 5 plus 1 divided by 3, 2, 5, 2. And then 5 changes into 2 times 2 plus 1 divided by 5, which is 1. And then finally, each of the 2's changes into 1 plus 1 divided by 2, which is 1. Okay, so we came back where we started. Yeah, I mean, you could have guessed it by the word periodicity. Okay, so we came back where we started. Let's try it one more time. Let's try it for a smaller path, but now we will write the variables. Okay, so let's try it like this. Let's say we have just this very short path. We start with x1 here, x2 here. Oh, wait, I called them xy. Let's call them x and y. Well, first, I guess let's start with white one now. It doesn't matter which one you start with. So first, this x will change into y plus 1 divided by x. And this y stays the same. Yeah. And then now this y has to change. So this one stays the same. And y changes into y plus 1 divided by x plus 1 divided by y, which is x plus y plus 1 divided by xy. Yeah. Okay, and we just keep going. Okay, so next one will be, so this one will stay the same, xy, but this one will change. And this is the most fun one. So if you add one here and divide by this, you will get this. And then if you add one here and divide by this, you will get this. And then finally, on the last step, you will get x, y like this. So you see, you didn't quite get back x and y. You got y and x, but if you do it 5 more times, you will get x, y. So it will come back like for real. Just a second. Okay, so basically around year 1991, Zamolodchikov noticed that this works. And by noticed, I mean like noticed. He didn't prove it. So proof. In fact, he noticed it in a slightly bigger generality, which I will tell you soon, right? So not just for path. It's some who work slightly bigger generality. But let's say just for path, it was proved. It was not proved until 1995. Even though people got interested in this and tried to prove it. In fact, it looks like some kind of math Olympiad question. Like you can explain it to, I don't know, 7th graders. Like it's very easy to explain. It looks like math Olympiad problem. You just start with paths of arbitrary lengths. You start doing this process. Eventually, numbers come back to where they started. It took people 4 years to prove it. It wasn't easy. you could ask, how did he notice? What was he working on? So Zamolodchikov is a physicist. He's still alive. He's a physicist. Uh, he was working on some kind of physics. I tried to read his paper. There are physics papers which I can understand a little bit. I couldn't understand almost anything in his paper. I encourage you, I will eventually maybe share with you a link to his paper. You can find it yourself. Uh, Try reading it. If anybody can read it and explain to me what's going on there, it's very, I mean, I couldn't do it. Like, okay, so it's very hard to understand what he was doing, but people got interested in this and it was hard. People couldn't prove this. So, okay, so in fact, as I said, he did it in a larger generality. What do I mean by this? Well, does it work for other graphs? So let's take bipartite graphs, right? So we can color them black and white. And we don't have to take paths. Like, I don't know, here's one graph. Here's graph number one. I don't know. You can come up with like, here's a graph number two. Here's graph number three. Etc. You can take all sorts of bipartite graphs and play the same game, right? You just use the same formula. Uh, Anybody who doesn't know, do you want to try to guess for which of those it works, for which of those it doesn't work? The ones on the board.
Probably for the first one.
For cycles,
You think it works for cycles?
I
Or
think
doesn't
no.
work? So yes or no?
I think no.
No, yeah, it doesn't work for this guy. How about those two?
It
I
works.
think that it works for left, but does not work for right.
Yeah, it works for left, but it doesn't work for the right. So, but why does it work for this one, but not for those two, right? So which ones are the ones for which it works? So by the way, let's try it. Let's try it just to see how it works, how it doesn't work. So let's try, let's try this one. Let's just try it with numbers. Okay, so let's try, I'll write it like this. Let's try all ones again. Okay, so this is my beginning 1, 1, 1, 1, right? And the one in the middle is the white one. Okay, so let's say if I do the black ones first, all of them become twos. Now I do the white one. I have 8 plus 1 divided by 1, which is 9. Now I do 9 plus 1 divided by 2, which is 5. Does everybody understand what I'm doing?
Yeah.
Ask me if it's confusing. People okay with it? So yeah, so now I need to do the middle one again. So I do 5, 5, 5, 125 plus 1, 126 divided by 9. 126 divided.
14.
Yeah, 14. So it will be 14, 5, 5, 5. Now I do 14 plus 1 divided by 5, which will be, I'm running out of space, so it will be 3, 3, 3, 14. And now I do 27 plus 1 divided by 14, which will be 2. So I get to 3, 3, 3, 2. And then now I probably get 2 plus 1 divided by 3. I get into you know 1, 1, 1, 2. And the last one I will get back into 1, 1, 1, 1. Yeah. Okay, so we came back. Everybody saw we came back? Okay, let's try it with the other one. Let's try it with the other one. With the other one looks the same, except it has 4 petals. So the other one looked like this. So let's try the same thing. 1, 1, 1, 1, 1. This becomes 1, 1, 1, 1, 2. This becomes 3, 3, 3, 3, 2. Tell me if I make a mistake. This is not in my notes, so I could make a mistake. Now this becomes 81 plus 1 divided by 2, 41, 3, 3, 3, 3. This becomes 42 divided by 3, 14, 14, 14, 14, 41. And this becomes some really huge number. And if you do it a couple more times, you will see it doesn't look like it comes back. So it's just numbers keep growing. So it doesn't. So in this case, it doesn't come back. But why such a difference? Why 3 petals it comes back and 4 petals it doesn't come back? Okay, so okay, let me try to give you one reason why such a difference. Any quick questions so far? Okay, no quick questions. So
sorry, I have a quick question. So do we look only at bipartite graphs here, right?
yes. So the way this is defined is only for bipartite graphs. Yeah. Let's make our life simple. Only do it for bipartite graphs.
And I have one small another question.
Yeah.
Do our colors correspond to orientation of edges in the graph somehow?
So far, there is no orientation.
Okay.
So far, it's just a bipartite graph, not oriented graph. No orientation.
Okay, thank you.
Yeah, so far.
One aim to have is that it can be colored by two colors, yes?
Yeah, bipartite just means can be colored 2 colors so that all edges connect black to white.
Yes.
So there is no
Yes.
black or white.
Okay.
That's bipartite. Okay, so here's the definition. A bipartite graph has sub-additive labeling. Sub-additive labeling. If we can assign each vertex B a number f of B, which has to be a positive number, such that the following condition holds. Twice f of V is more than the sum over all neighbors of V, right? All U connected to V, f of V. Okay, so it's a little strange definition, but let's try an example. Yeah, let's just take this graph over here. I will put numbers 2, 3, and 2. Right, so I assign to each vertex a number, a positive number. And let's check. So twice this number should be bigger than the sum of all neighbors. Sum of all neighbors is 3, twice this number is 4. Correct. Twice this number, 6, bigger than 2 plus 2. Correct. Yeah, so that's the condition. For each vertex, this must be true. If this is true, such labeling is called subadditive labeling. So it exists for this graph. Okay, so I claim it exists for this graph. Can somebody tell me subadditive labeling for this graph?
We can take 2 and then 1 plus epsilon for some small epsilon.
Like this, 1 plus epsilon, 1 plus epsilon, 1 plus epsilon.
Yes.
That works. Yeah. We can also just do something like this. My example is just 3, 3, 3, 5. That also works. Okay. But now I claim, here's my claim.
Is it true that it exists only for trees?
No. For example, I claim that this doesn't exist for this graph. This graph does not have a subadditive labeling. Let's try to prove it. So look, let's call those x1, x2, x3, x4. And let's call this one y. If it existed, what we would know? We would know that twice x1 is bigger than y, right? Everybody agrees? And the same for the other one. Twice x2 bigger than y, twice x3 bigger than y, twice x4 bigger than y. But if we add them all up, we will get that twice sum of those is bigger than 4y. Or in other words, sum of those is bigger than 2y. But that's exactly should be the other way around, right? 2y should be bigger than sum of the neighbors. Yeah. Okay, so this one doesn't work. And now you can probably guess where it's going. So theorem proved by my courser Pavel Galashin and me is that to have the Zamolodchikov periodicity, to have this property, bipartite graph must have subadditive labeling. So I will not tell you how to prove it. It's a little painful to prove it. You need to consider some kind of tropical version of this dynamics. It's not horribly hard, but it will take time to prove it. But the theorem is the following. Theorem to have this kind of periodicity, right? And by Zamolodchikov periodicity, I exactly means that you start with bipartite graph, you apply this dynamics we applied, and you get a periodic map, right? So eventually it comes back. So to have this map periodic, the bipartite graph, and we only consider it for bipartite graphs, right? So graph must have subadditive labeling. So this one has subadditive labeling, so it has a chance. This one does not, so it has no chance. This one will not be periodic. It still doesn't prove that the ones which have such labelings are periodic, but it says that all the other ones are not. Yep.
Can you say, please, what is subadditive labeling?
Yeah, I just defined it before I erased it. So subadditive labeling is labeling which satisfies this property.
Okay.
Right? So subadditive labeling is just labeling of vertices by positive numbers such that each vertex this property holds, just like we were doing now. And as the theorem says, if you don't have such a labeling, then you will not be periodic. Your associated, the system is called T system. So your associated T system will not be periodic. Okay. So far, so good?
So in this definition of subadditive labeling, you don't really use the bipartite structure, right? So you can, in principle, give this definition for any graph,
That's
right?
true. In
Okay.
principle, you could use this definition for any graph. Yeah, somebody else has question?
Yes, and this theorem states only a necessary condition, or it also can be
That's right. So
stated.
it's only necessary. So it's also sufficient, but so far I stated it as only necessary. Yes.
Ah, okay, thank you.
Yeah. Good. Any other questions? So I will not prove it, but I can give you sort of intuition why this has to be true, because it seems to be a bit random. Why those subadditive labelings would be related to this kind of periodicity. And kind of intuition is like this. If you're periodic, then you have a fixed point where all initial numbers are bigger than 1. That's the technical condition. So, right, so if you're not periodic, you expect that it will grow and grow and grow somehow. But if you're periodic, then it somehow doesn't grow, it comes back. So it's not unreasonable to think that somewhere in the middle there is a fixed point. Right, and then if you start with all numbers equal to 1, the next step, they will all be bigger than 1. So it's not unreasonable to think that there is a fixed point where the all numbers are more than 1. And now if you found such numbers, so by the way, how do you find such numbers? For example, let's say this is our graph. What does it mean to find such numbers which are fixed point? You just solve some quadratic equations or some kind of equation. So for example, here, I think this works. Square root of 3, 2, square root of 3. That's a fixed point where all numbers are bigger than 1. Let's check it. Product of neighbors plus 1 is 3, divided by this guy is this guy himself. Everybody can see it? Okay, let's try this guy. Product of neighbors 3 plus 1, 4, divided by this guy is this guy himself. Yeah, so this is a fixed point. So it's not so intuition is if you are periodic, you will have some fixed point like this. And then you just take logarithm. If you take logarithm of fixed point, if your xi squared is equal to product of all the neighbors j xj plus 1, right? That's what it means that it's a fixed point. For each I, xi times itself is equal product of the neighbors plus 1. If you were to take logarithm of that, you would see that twice logarithm of xi is bigger than sum of the logarithms of all those xj. So basically, logarithms of those numbers would give you subadditive labeling. Okay, that's roughly the intuition. That's roughly why, if you would expect that if your system is periodic, then it would have a subadditive labeling. It would have a fixed point, and logarithm of it would be subadditive labeling. Now, why do we care about this? Right. So in some sense, you could say we reduced one problem nobody knows the answer to another problem nobody knows the answer to. Right. So we had to say we're looking for graphs where something's periodic, and now we are looking for graphs which have some labeling. God knows which graphs have this labeling. Okay, so the reason why it's better is that those graphs which have subadditive labeling, they're super famous. They're superstars, they're most famous graphs in all of mathematics. Okay, so let me tell you. So here's a statement. Here's a statement. Super famous. That's a precise mathematical statement. Super famous. They can be classified. You can say which graphs have subadditive labelings. Can be classified. And the answer is the famous ADE Denkin diagrams. Okay, I don't know how many of you heard of this, but like I think at some point, like I think at MIT there's this professor Pavel Etingov. I remember once him saying that if we were to send proof of life on our planet to aliens, we should encode those graphs for aliens and send them. Like it would prove that there's intelligent life. So what are they like? First of all, they're very easy to draw. So there's two infinite families and three exceptional cases. The infinite families, one of them is what we already saw, the path, which is called AN, right? So path of with n vertices is called type AN. The second infinite family is path with a fork at the end, right? So this is called DN. And then there is three exceptional cases. One, two, three. And so those are E6, E7, E8. Okay, if you've never seen those, you should meet them. You will see them, if you do math, you will see them probably for the rest of your life. Like those are very important graphs. They classify many things, right? So they classify semi-simple algebras. They classify simple plane curve singularities. They classify a bunch of other stuff. So in fact, it's one of the big mysteries of mathematics why those particular graphs come up in many places, sort of as classifications of things. But yeah, so here's the theorem. So now that I drew for you those pictures, let me state the theorem. Theorem by Wienberg. Those are the only graphs with subadditive labelings. So they have subadditive labeling and nobody else has subadditive labeling. Any questions about it?
Actually, can it be proven by simple algebra? Because
we will
seems
prove
like
it
it
by
can.
simple brute force. We are about to start proving it by simple, like, I don't know,
Yeah, because it
brute
seems
force
to.
combinatorics. So can it be
It's
proved by algebra? Yeah, I think so. There is some representation theoretic meaning to those stability functions, but like unless I don't know what do you mean by simple algebra?
no. By simple algebra, I exactly meant like combinatoric. I mean like school algebra, not like algebra.
Yeah. So that's what we're gonna do. We're gonna just start proving it by brute force. In fact, I mean, we will try. I mean, we will start it. We will see how much. It's not super hard. It's a little technical. There are a couple of lemmas. I mean, I will show you. So, uh, but let me think. How much time do we have? Okay, let me just start showing you how to prove it. And then I will leave it as one of your exercises to finish the proof in detail, okay? So here's, I mean, right, so first of all, just to find a labeling for those graphs, it's a small exercise. It's easiest for the path, I think. For the path, I think for the path, you can always just do like 2, 3, 3, 3, 2. Can't you always just do that? Yeah, I think you can always just do that. Like 2 bunch of 3s, 2. I think this. So the harder part, of course, is to
Wait, sorry,
to
but
prove that
but
nothing
for the
else
three,
works. Right. So there's 2 parts. Why do those guys work? Why do they have subadditive labeling? And I mean, it's a little like we need to think a little for E8. What is the subadditive labeling for E8? But the harder part is, of course, why nothing else works. Why are they the only ones? Okay, so here's roughly how you would go with a proof. Lemma 1. Cannot have vertex of degree 4. Of degree at least 4. And we kind of already proved it. Remember, I did this computation for you. If you have something like this, you write inequalities here, 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 and this contradicts inequalities there. Yeah. So it's not hard to prove that if a graph has subadditive labeling, it cannot have vertex of degree 4 or more. Does it make sense, or do you want me to show it again?
No, that's fine.
It's fine. Okay. That's lemma 1. Lemma 2. Okay, so now we know we don't have vertices of degree 4 or more. You know, if you have only vertices of degree 2 or less, then you have a path or a cycle. So that's easy. So the only interesting remaining thing is what if there are some vertices of degree 3? And the second lemma says we can have at most one vertex of degree 3. At most, one vertex of degree 3. Okay, this one is a little tricky, not very tricky. So imagine we have 2 vertices of degree 3. They would have to be connected, right? Our graph is connected. So let's take 2 neighboring vertices of degree 3, meaning that they are connected by a chain of vertices of degree 2. So just take 2 vertices of degree 3, such that between them there is no vertex of degree 3, right? You can connect them, but everything in between is degree 2. So you have some picture like this. Maybe that it goes further. I don't know. But you have some local picture like this. Well, let's think about those numbers A, B, let me call this one C1 and C2. So here's what I want to say here in this situation. My notes say that 2A is bigger than C1. Do you believe that? Right, because twice A, right, it's a subadditive labeling. Twice A should be bigger than the sum of neighbors. A might have some other neighbors too, but the sum of neighbors is at least as big as C1, right? So 2A should be bigger than C1. Everybody agrees with this? Okay, now similarly, 2b is bigger than C1. But we can also say that twice C1 is bigger than A plus B plus C2. Okay. So this is just from definition of subadditive labeling. Now, if we combine those in the right way, and what do I mean by right way? Let's divide those 2 by 2. Okay, so this is more than half, this is more than half. Add them up, cancel out, we'll get C1 is bigger than C2. Okay, so we conclude that C1 is bigger than C2. Now you can check that this also means that C1 bigger than C2 would mean that C2 has to be bigger than C3. Because if those both are bigger than C2, then twice C2 cannot be bigger than their sum. And this just keeps going until you reach the other side, all the way up to here. But you could have done the same thing on the other side. On the other side, you could do the same argument, and you would see that this guy has to be bigger than this guy, and that's a contradiction. Okay, so something like this. Okay, so that's how you get a contradiction from this picture, and therefore there is at most one vertex of degree 3. And after this is just slightly painful consideration of cases, right? So you say if you don't have vertices of degree 3 at all, then it's easy. It just has to be a path or a cycle. You check those two, and if it has vertex of degree 3, you just need to consider cases how long those arms are. All right, so you say that, like, first of all, it's impossible for all 3 of them to be more than 2 in size, and then if one of them is 2 in size, what can the other ones be? Something like this, and you just find that it has to be either type D or one of the E's. Okay, so slightly painful, but can be done. It will be your homework. You know, it's a nice thing for once in your life to work it out. I mean, this is such a famous thing. It's satisfying to work it out once in your life. Okay, so this will be exercise number 1. And I think Sylvester might help you finish this off during your TA session. So exercise 1 is to finish this proof, basically. Okay, exercise 2. Here's a slightly fun variation of this, which actually is important. We can define weakly subadditive labelings. What's that? It's just like subadditive labelings, except the inequality is weak. Is greater than or equal sum of all the neighbors . Okay, so it seems like there isn't much difference. You could say, so what? But for example, remember this guy didn't have subadditive labeling. Well, guess what? He does have weakly subadditive labeling. This is a weakly subadditive labeling of this guy. So if you allow yourself equality here, you allow yourself more graphs. And those graphs will be important for us. They will not be Zamolodchikov periodic, but they will be something else. I will tell you what they are one of the next lectures. So exercise 2, classify those. right? So just like we classified the ones which, well, we know the answer for, so ADE Dynkin diagrams are the answer for the graphs which have strictly subadditive labeling. Find and prove the answer for the ones which have weakly subadditive labeling. Right, so for example, this one works now, but this one will still not work. This one doesn't have weakly subadditive labeling. This one works, this one still doesn't work. So what's the conclusion from all of this? Let me tell you a bit about what's the conclusion so far from everything I told. To have periodic system, you must be ADE graph. One of those ADE Dynkin diagrams I drew for you. Okay, right, so that's the first conclusion. And in fact, this was the original conjecture of Zamolodchikov, right? So I told you he did it not just for path. His original conjecture was this was conjecture by Zamolodchikov, was that this works for any ADE Dynkin diagram. He didn't care if there are any other graphs, right? This is later theorem by Pasha and me that there is no other graphs for which it works. But his conjecture was that just it works for those graphs. ADE T-systems. So I never wrote definition of T-system. T-system is what we were looking at, right? That's T-system. ADE T-systems are periodic. So as I said, so in type A, which means that's just for the path, this was proved by Frankel and Janesh in 95. And for all ADE types, it was proved by Fomin and Zelinsky in 2003. Right, so it's a pretty long time, right? The original conjecture was 1991. So, and it was pretty popular. People actually, it's not like nobody tried. People actively tried to prove it, and it took 12 years and kind of discovery of cluster algebras to prove it in general. Okay, so I think this is where I want to stop today, and we also kind of out of time, but I'll keep telling you more about this and further developments, et cetera, et cetera. So there are more general versions of this conjecture, which are interesting. So I'll tell you more next time. It will be interesting. Come back. I don't know. Any questions about any of this?
Are
But
we
it's not
having
conjecture anymore. It's
restrictions?
proved now.
Are we having restrictions to our homework regarding type of proof, basically?
Say it again. Say it again.
Do we have any restrictions regarding this exercise and regarding basically the type of proof?
I just don't care so much.
Oh, okay.
I was told that I should give you
Thank you.
exercises, so I'm giving you exercises, but also it's a nice exercise to work out. It will actually teach you something about this. So work it out in the best possible way for you, but I mean, you can talk to Sylvester, who'll be, I guess, checking your proof, but I don't think we are going to be very strict with what we want from you. Yeah. Any other questions?
Yeah, I have a question. So where do we have to submit our homework? Like to send email or?
Yeah, that's a good question. I don't
Yeah,
know.
I can answer this question. Yeah, you can just send your as for those people who were before in our courses, you know that you can send directly homework to you to the TA with the your name and
Yeah. So our TA is Sylvester Zhang. He's over there.
Sylvester is here.
Yeah.
Thank you, Sylvester, very much.
So
And
I
I
think they might not have his email yet, so somebody will have to tell them his email, but
they do. I think
they do.
so.
Okay.
There will be emails sent in a few minutes. I mean, I think Andre will send you, as usual, the email with the link for the Zoom meeting for the problem class, as well as with the information where to submit homework and the email and everything. So
Okay.
just wait. Everything is going to be sorted out. I wanted to thank again Pasha for a wonderful lecture because I actually didn't plan to stay for a long time, but I was so interested that I stick around and actually
Okay,
listen.
thank you. But any other question? Anybody else had questions? I can.
I also have a question.
Yeah.
What you just showed, it's really like the fact that you prove is are really similar to what we did when proving classification of primitive root systems. Are this connected to them, or is it just
Right.
or is it just coincidence?
So that's a good question. I mean, it goes back to the fact that so many different questions have the same answer, which is this ADE. But specifically, so the reason those T systems are periodic for ADE is because they will live inside finite type cluster algebras. And finite type cluster algebras, they kind of, you know, they're kind of based on a finite root system. So somehow it's connected like that. But do I know a direct way to connect why there is the same classification of subadditive graphs, labeled graphs, and finite, crystallographic root systems? I'm not sure I do. I don't think I do. I don't know like a very direct way to connect it. I don't.
Okay, thanks.
Yeah.
I have one more question. So here we're looking exactly at the bipartite graphs. What if instead we will look at the graphs which can be colored in 3 colors, 4 colors, more?
There
So
is
and try to do the same procedure. So we look at first color, change first color, second, and so on, and then just repeat it.
there. So right. I know of a generalization of this thing for 3 colors for very specific graphs, and I can show where it is. It would be better if we wait till after 1 or 2 more lectures. You should ask me this question after my second or third lecture. But it's an interesting question. What kind of generalizations this kind of admits? And yeah, as I said, I know one such generalization, which involves 3 colored graphs. But that's the only one I know, and it's very rigid. So there could be more. There could be more interesting ones. Um, yeah. So at the end, I will try to tell you what are the sort of open questions which I think are interesting, and that could be one of them. Yeah, I will show you some what I think are.
All right. Thank you so much.
Yeah. Okay. Okay. Thanks, everybody. Oh, wait. Somebody else has a question. Yeah.
Yeah. Does there exist some purely geometrical or topological way to look at this periodicity and or at those graphs?
There is a representation theoretic way to look at it, coming from categorification of cluster algebras. This is like way beyond. I mean, I don't think I could teach you that. You definitely wouldn't have time for that. So I don't know a purely. So I will teach you one. There is something geometric I will say during our third lecture. But in principle, I would say the probably the answer, if I understood your question, probably the answer is no. The closest somehow to realizing this whole thing is that, like, where does it live? I mean, the closest to this is the original paper of Zamolodchikov. For him, it lived in some kind of physics. And as I said, it was extremely painful to try to read. I mean, I've read some physics papers in my life, and it went okay. But this one, I like literally every word of it. I was like, I don't know what this means. And like, so yeah, I don't know. The closest to geometric or topological would probably try to read his physics paper, but I failed at that. Oh.
Okay,
Yeah.
thank you.
But cluster algebras, they provide the categorification of this whole story. So that I will tell you a little bit more about that. And so that in a way is geometric algebraic or whatever way to look at it.
So when you say categorization, you mean representation theory of some algebra, quiver, or
Yeah, so there's this thing called cluster categories. So they take quiver and there's like representation theory, like representations associated to it, and they enrich it a little bit, and they call it cluster category. And inside this cluster category, this kind of process over here has some meaning, and then they prove that whatever the meaning it has. So something like that. They look at representations of quivers. Basically, that's where the whole thing lives. Like you have a quiver, which is just a directed graph, and they look at they put vector spaces at its vertices. They take maps between them, etc. It's just like a whole science. And they so at some point they figured out that if you just tweak a little bit something they already knew in the science, you get categorification of cluster algebras. It's called cluster categories, and they use it a lot in this and many other things for cluster prove things about cluster algebras, etc., etc.
okay, thanks.
Okay. I mean, you'll have more chances to ask me. So nice seeing you, everybody. Nice meeting you. See you, I guess, on Thursday, right? Our next class.